So, if you're taking a second semester organic chemistry class, you need to be familiar with this hierarchy, with this order, where this acyl chloride is the most reactive. It's the most reactive out of these 5 compounds because it has the most electrophilic carbonyl. And then comes this acid anhydride. This acid anhydride is the second most reactive because it has the second most reactive, most electrophilic carbonyl carbon. And then this ester is the third most reactive, then comes the amide, then comes ketones and aldehydes. So we have this hierarchy of reactivity where, again, the acyl chloride is the most reactive. Then again, these ketones and aldehydes are the least reactive. And something else you need to be familiar with is this hierarchy of stability of these leaving groups, where, again, this chloride is the most stable leaving group. Then comes the acetate, then comes this methoxide, then etc. So we have this hierarchy of stability of these leaving groups, where, again, this chloride's the most stable leaving group. Then as you go downwards, it gets less stable, so therefore this carbon anion is the least stable. So again, we have these hierarchies, and this is one of the reasons why we have this hierarchy of reactivity. Because again, when they react, they form very stable leaving groups. But again, the point is we have this hierarchy of reactivity where this compound's the most reactive and this compound's the least reactive. And there are some important implications. The fact that we have these differences in stabilities of leaving groups has some very important implications. And one of them is, for example, let's say we have the acyl chloride. Then if we had a solution with these acyl chlorides, we would be able to produce any compound below it. If we had a solution with these acyl chlorides, we could form acid anhydrides. Or if we had a solution of acyl chlorides, we could form esters, or we could form amides, or etc. So you can always go down the hierarchy. And again, maybe we had a different solution with these acid anhydrides. Well, again, if we had a bunch of these acid anhydride compounds, we could use them to produce any compound below it. But something else important to realize is we can't go upward. For example, let's say we had a solution of these amides. Could we produce these acid anhydrides? Well, no. You can only go downward. If we had a solution with a bunch of these amides, we could only produce the ketones. We couldn't go upwards. So again, the point is we have this hierarchy of reactivity, where this acyl chloride is the most reactive, this ketone is the least reactive, this chloride is the most stable leaving group, and this carbon anion is the least stable leaving group. And then again, you can always go downward. If, for example, if we had an ester, we could form all the compounds below it, but we wouldn't be able to form the compounds above it. So why is this? What's going on? Well, let's say we have a solution of these acyl chlorides. So let's say we have a solution of these acyl chlorides. And let's say with these acyl chloride compounds, let's say we want to form esters. Can we do that? Well, yeah, because we can go down the ladder. So if we have a solution of acyl chlorides, we could go down the ladder and we could produce these esters. So how would we do that? Well, again, let's say we had a solution of these acyl chlorides, and let's react them with this methoxide nucleophile. What would happen? Well, we know we go through a nucleophilic acyl substitution where, again, the nucleophile nucleophilically attacks this carbonyl carbon, which we already learned in previous videos, very electrophilic, and then we push these pi electrons up onto this oxygen. And when we do that, what happens? When we do that, we know we form this tetrahedral intermediate. We form this tetrahedral intermediate where, again, we attacked. So when we attacked, we formed a bond. When we did that, we pushed these pi electrons up to the oxygen, and now we have this oxygen anionic tetrahedral intermediate. So now we've learned in previous videos what happens next. Then we know the electrons will fall back down. When they fall back down, they form a double bond. But when they form that double bond, we know we're going to break one of these bonds. We're either going to break this bond, or we're going to break this bond, or we're going to break this bond. So which bond are we going to break? Are we going to break this bond, or this bond, or etc.? Which bond are we going to break? Well, again, let's imagine, let's do an example. Let's say the electrons fell down and they broke this bond and the electrons fall on the chlorine. What would we form? We'd form these products with this chloride leaving group. So that's one option. Or another option is, again, the electrons could fall down, forming a double bond. And when they do that, they could break this bond. And if they broke this bond, the electrons would fall down. We would form these products with this methoxide leaving group. But again, which one is the most stable leaving group? We know this chloride is the more stable leaving group. So we know nearly 99% of the time, once we form this tetrahedral intermediate, we know this is the bond that's going to be broken. This is the bond that's going to be broken because this is the better leaving group. So this is nearly every single time, this is the bond that's going to be broken. These electrons fall on this chlorine, and we're going to form this product. So the point is, whenever we form this tetrahedral intermediate, and we have bonds that can be broken, and we have a choice which product are we going to make, we're always going to make the product that's below, that's down, that's going to go down the ladder. And again, it's because of the stabilities of these leaving groups and the options that are going to be made. But again, whenever we form the tetrahedral intermediate, where we have an option, we could go down two paths. We could either break this bond or this bond. We're always going to break the bond with the better leaving group. So therefore, we're always is going to essentially form the product out of the two possible products. We're going to form the product downward. So that's why we can always go downward. But now let's do a different example. Now let's do a different example where let's say we have this reaction. Let's say we have this reaction. So let's make some space. But now let's say we had this compound, this ester. Let's say we had the ester, and let's say we wanted to go upward. Let's say we wanted to form the acyl chloride. Well, we already know you can't do that. With this ester, you could form all the compounds below it, but you couldn't go upward. So why is that? Well, let's try. Let's say we have the ester, and let's try to form the acyl chloride. So we have a solution with the ester, and we reacted with the chloride nucleophile. Again, same thing. We nucleophilically attack. When we attack, we push the pi electrons up, and again, we form this tetrahedral intermediate, where again, when we attacked, we formed a bond represented by this bond. Then we push the electrons up, and again, we form the tetrahedral intermediate. But again, we know whenever we form this tetrahedral intermediate and we have options, we know we're going to form the compound below. We're going to form the compound below, and we know, so therefore, with these two options, we know we're going to form this product. We're going to form this product because again, this is the better leaving group, so this is the bond that's always going to be broken. So again, we know because this is the bond that's going to be broken, we know what's going to be left is this guy. So again, we're always going to, when we have an option with this tetrahedral intermediate, we have options, and again, we're always going to produce the compound below it. So again, this is the bond that's always going to be broken, so we're always going to make these products, so we're always going to make this product. So again, now we're back where we started. We had the ester, now we're still at the ester. We were ineffective, we were unsuccessful in producing the compound above it because of this principle and due to these reactivities of these leaving groups.